Thank you very much. Sponsor natin no, kay Dashlane. So that's the first video. No? So let us now continue on the classifications of computer architecture na pin-repair ko din naman. Or not totally pin-repair but sinerge ko sa internet. Okay.
Well, hello everyone. Welcome to this session, and as promised, in this particular lecture, we are going to dive right into various classifications of computer architecture. So, without any further ado, let's get to learning. Now, coming to computer architecture's classifications, there are various models. Among them, we will be learning about two most popular approaches. So, let's start with the first one. Computer architecture is broadly classified into specifically two categories: von Neumann architecture and non-von Neumann architecture. Now, von Neumann machines have the following characteristics. It has three basic hardware subsystems: the CPU, the main memory, and the I/O system. Moreover, it must be a stored program computer. That means the main memory system holds the program which controls the computer operation, and the computer can manipulate its own program more or less. Also, it can do the same to any other data stored inside the memory. Furthermore, it carries out instructions sequentially, so the CPU appears to execute one operation at a time. Well, the major debate has always been about having a single path between the main memory and the processor proposed by this very architecture. Now, already in our previous discussion, we came to know about von Neumann's professorship at Princeton University, and that is the reason why this architecture was also referred to as Princeton architecture. Now, people from Harvard University proposed another model, which adopted most of the features proposed in the Princeton architecture, except for the fact they used two different memory units and thus pioneered parallelism. This is popularly known as Harvard architecture. Let's try to understand the need of it. First of all, systems having pure von Neumann architecture stores the instructions and the data in the same memory unit. Thus, both the data and the instructions are phased over the same path. This means the processor can't simultaneously read an instruction and operate on data. This phenomenon is known as von Neumann bottleneck and was first officially discussed by the great John Backus, inventor of Backus normal form for context-free languages, during his 1977 ACM Turing Award lecture. Next, there is modified Harvard architecture, which cannot completely be classified as von Neumann architecture as it doesn't strictly follow the von Neumann principles. But it is more of a combination between both the Harvard and the Princeton architecture. Now let's study them in a bit details. Now in Harvard architecture, we have separate memory units. One is for strictly storing the instructions and the other for the data items. This way, the processor can both read an instruction and perform data memory access at the same time. Therefore, computers belonging to this architecture family are faster because instruction fetches and data accesses are not competing for the single memory pathway anymore. Now, coming to modified Harvard architecture, it is very much like the Harvard architecture itself. However, it relaxes the strict division of instruction memory and data memory. Here, the processor is accompanied by a small yet fast memory storage called cache. When the processor is executing from the cache, it acts as a pure Harvard architecture, and when it is accessing from the backing memory, it acts like a pure von Neumann machine. This modification is widespread in modern processors. So this was the first approach of classification of computer architecture. Let's move on to the next one. In this model, computer architectures are classified by a variety of characteristics, including the number of processors, the number of programs they can execute, and the memory structures being used. The first group is SISD, that is single instruction stream, single data stream. The von Neumann architecture belongs to this specific category. SISD computers have one CPU that executes one instructions at a time. Hence, single instruction stream, and fetches and stores one item of data at a time, hence single data stream. The next group is SIMD, that is single instruction stream, multiple data stream. Processor array falls into this category. SIMD machines have a control unit that operates like a von Neumann machine that executes a single instruction stream, but they have more than one ALUs. The control unit generates the control signals for all the ALUs which execute the same operation on different set of data items, generally in lock steps, hence multiple data streams. The next group of computers are MISD, multiple instruction streams, single data stream. Logically, machine of this class would execute various different programs on the same data items. This group doesn't have any particular practical implementation. Nonetheless, some machines belonging to the next category can be used in this manner. Alright, the next and the final type is MIMD, multiple instruction streams, multiple data streams machines. These are also known as multiprocessors. These are comprised of more than one independent processors and each one of them can execute a different set of instructions, hence multiple instruction streams, on its own set of data, hence multiple data streams. Now this classification was proposed by Michael J. Flynn in 1966. Since then, it has been used as a tool in design of modern processors and their functionalities. That is why it is also known as Flynn's taxonomy. Alright folks, that was the two most popular classifications of computer architecture. Hope you liked it and learned something new. I'll see you guys in the next one. Thank you all for watching.
So you were able to have the grasp of the various computer architecture and how the processor is being on how processors execute instructions. Okay, with the fetch, decode, execute cycle, and the different classifications of computer architecture. So let us now continue our discussion. Before it, no, let us continue our discussion on the brief history of computers. So we have four generations of computers. We have the vacuum tube. We also have the transistors, the integrated circuits, and the microprocessors. No, in first generation we have the vacuum tube. When we say vacuum tube, no, we use vacuum tubes for digital logic elements and memory. No, designed approach first implemented in the IAS computer is known as the stored program concept. So here's the structure of the vacuum tube. We have the main memory, the arithmetic logic unit, the control unit, and the input-output equipment. So kung mapapansin ninyo, meron tayo rito yung katulad sa may von Neumann architecture, the Princeton architecture wherein the structure has a main memory. Di ba? Meron din tayong ALU, the arithmetic logic unit. The control unit that is being the processor of the instructions decoded by the fetch cycle and the input output equipment. No? If you can notice dito sa right side natin we have the IAS structure wherein mapapansin ninyo ito ang laman ng CPU natin or the central processing unit. Meron siyang ALU. When we see ALU, this calculates the binary inputs and outputs of an instruction. We have the ones and zeros here. We have the ALU units or the circuits. And the following, on the other hand, is the main memory. Di ba? Nakalabas dyan yung main memory, nakalabas din dyan yung I/O. But within the CPU, we have here the ALU and the control unit. When we say control unit, again, dito pumapasok yung mga instructions na nagbibigay ng instruction din naman sa ALU whether to add, to store, to jump, or to move the instructions in various addresses. Okay? Again, kinukuha niya yung data, instructions niya dito sa main memory. Okay? Meron din tayo rito iba't ibang mga acronyms. We have the AC, the MQ, the MBR, the IBR, PC, MAR, and IR. So yan ang laman, the idea there of the vacuum tube. Meron siyang, again, we have here the CPU, the input output and the memory. Okay, so that's how vacuum tubes are being designed, no? Or that's the architecture of vacuum tube before, no? Sa mga basic computers natin. Meron siyang main memory kung saan nandito yung instructions and the data. We have the ALU, the arithmetic and logic unit. Dito yung operations ng binary data natin. The control unit naman, nandito yung interpretation or decoding of instructions from the memory and cause it to be executed. And last is the input-output equipment operated by the control unit. So that's vacuum tube. No? The next generation is the transistor. Ano naman ang tinatawag na transistor generation? In transistors, no, the transistor is smaller, cheaper, and generate less heat than the vacuum tube. No? It can be used in the same way as a vacuum tube to construct computers. No? Unlike the vacuum tube, which requires metal, which requires wires, metal plates, and glass capsule in a vacuum, the transistor is a solid-state device made from silicon. The most important of these is the use of data channels. A data channel is an independent I/O with its own processor instruction set. Another new feature is the multiplexer, which is the central termination point for data channels in the CPU and the memory. The multiplexer schedules access the memory from the CPU and data channels, allowing these devices to act independently. So dito sa transistors, sa second generation ng computer, instead nagagamit sila ng vacuum tube, gumagamit na sila ng transistor. So ang transistor kaya ginagamit kasi mas maliit, mas mura, and yung heat dissipation niya is mababa, hindi katulad sa vacuum tube, no? At the same time, ang kagandahan sa transistors, meron ka ng iba't ibang data channels na tinatawag, no? At the same time, the new feature in the transistors is yung tinatawag na multiplexer. Multiplexer, it is a central termination point for data channels. Later on, we will discuss or we will be elaborate what multiplexer is and what data channel is. But again, the idea here in transistors, it is smaller, cheaper, and it generates less heat than a vacuum tube. So here in figure 1.9, I have here the CPU using transistors. No? It is developed and designed by the IBM, no? IBM 1794 computer, and meron na siyang kasamang mga iba't ibang peripheral devices. Okay, so here's the architecture. Nandito yung processing unit niya, meron siyang data channel puntang multiplexer, and yung memory may pupunta rin siyang data channel puntang multiplexer. Papasok sa multiplexer yung iba't ibang data channels natin na kumukuha ng instructions from IOs or the peripheral devices. We have the various line printer, card reader, card punch, and iba't ibang instructions yan. IO instructions. We have the disks, tapes, yan. So in transistors, we have added data channels na nare-receive naman ni multiplexer, and then binabato ni multiplexer sa CPU and sa memory for them to process the instructions coming from the input and output devices. Okay, so that's transistors. That's the second generation of computer using transistors. Okay, added na yung data channels niya, added na rin yung multiplexer niya sa kanyang central processing unit. Okay, so third naman, the third generation of computers, you have now the ICs or integrated circuits or tinatawag na microelectronics. No? Sa pagkakaalam ko, bago kayo makakuha nitong COA, Computer Organization and Architecture, meron na kayo nitong mga chips, no? Mga ICs sa electronics new subject. So, in ICs or integrated circuits, no? Since the beginning of digital electronics and the computer industry, there has been a persistent and consistent trend toward the reduction in size of digital electronic circuits. The basic elements of a digital computer, as we know, must perform data storage, movement, processing, and control functions. So dito sa ating third generation, or the ICs. Meron na siyang tinatawag na gate. A gate is a device that implements a simple Boolean or logical function. And the second one is the memory cell. It is a device that can store a bit of data. That is the device that can be in one of two stable states at any time. So one and zeros. So a gate, napag-aralan niyo na to sa may, saan ba yung mga may gates? Kay Ma'am Gal, no? Yung AND gate, NAND gate, NOR gate, OR gate. Yan. So these gates are now installed sa integrated circuits natin. Okay? So the trend nga, it is true naman that the trend, there has been a persistent and consistent trend toward the reduction of size of digital electronic circuits. So as you can observe, no, every time na maglalabas ng device or ng bagong version si Apple, lagi niyang ibinibida yung a billion transistors in a nano-sized architecture. Diba? So mas marami kang instructions, mas marami kang transistors in a smaller size. Lagi nilang ibinibida yan. Kung mapapansin nyo sa iPhone, sa MacBook, sa iPad, di ba? Micro size, nano size, kung anong sizes pa yan, di ba? Habang may lumalabas ng mga bagong devices or lumalabas na bagong mga hardware si Apple, lagi niya sinasabi yan, we have 1 billion transistors, we have 10 billion transistors, we have 100 billion transistors in a ganitong size. Ibig sabihin lang nun, mas marami yung gates na nakalagay, mas marami yung cells na nakalagay doon. Mas maraming instructions in a smaller size. So imagine this, kung meron ka 1 billion transistors pero hindi ganun kaliit yung size ng processing unit mo. So much as possible, yung billion transistors na yon, baka isang malaking kwarto na yon. Okay? So as you can, again, if you can imagine, no, yung mga processors ngayon, pag sinasabing 1 billion transistors, mas maliit. So pinagyayabang nila yung mga ganun. In such a way na mas maganda nga naman kasi hindi mo kailangan ng mas malaking device sa mas malaking mas maraming transistors, mas maraming transistors. Okay? So on the right side, meron ako ditong figure 1.11. We have here the wafer or yung mga, kung makikita nyo yung mga commercial ni Apple, yung parang bill or ni Intel ba yun? Intel yung processor niya parang gold. You know? Sa mga gold na yun, may mga boxes, may mga tiles. Those are considered as chips. No? Inside the chip, meron tayong mga gates. May mga gates tayo dyan. So this is the theoretical idea of a microprocessor or the IC. Ngayon naman, sa pagkakaalam ko, nakakita na kayo ng mga processors, no? Yan sa laboratory natin, marami tayong processors dyan. Okay? So there, every chip there, meron siyang mga gates na tinatawag. These gates, these devices can implement simple Boolean or logical functions. No? Since it has a billion transistors, it can now generate a billion instructions as well in a minute, in a second. Again, the instruction there or the basic function of the clock speed there is hertz. Meaning, if you can have a 3.2 gigahertz of instructions in 1 billion transistors, napakabilis na yan. So yan ang pinaglalabanan ngayon ng iba't ibang computer architecture companies like the Nvidia, the Intel, the AMD. No, meron din tayo sa Apple yung kanilang M2 chips at tinatawag. Okay? So those are the ICs or integrated chips or circuits installed within their processors, within their embedded systems, within their boards. Okay? So that's how you define integrated circuits or ICs na tinatawag. Meron siyang gate and meron na rin siyang memory cell. So here is the microprocessor. Just as the density of elements on memory chips has continued to rise, so has the density of elements in processor chips. As time went on, more and more elements were placed on a chip, so that fewer and fewer chips were needed to construct a single computer processor. A breakthrough was achieved in 1971 when Intel developed its 404. The 4004 was the first chip to contain all the components of the CPU on a single chip. So ito, cable 1.3, ito yung 4004 na microprocessor. No, magkakasama na dito iba't ibang component ng CPU. Meron na siyang memory, meron siyang memory, meron na rin siyang transistors, meron na rin siyang mga bus. Yung bus, again, ito yung data pathway, data channel ng mga instructions. Meron na rin siyang clock speed. Yan. And the year it has been introduced. So in 1971, the 4004 processor, meron siyang 108 kilohertz. So 108,000 instructions per second. No? 108 kilohertz. 108,000 instructions per second. So sa ano naman, sa buswidth naman, mas konti pa lang yung dumadaan na dito sa kanya. No? The number of transistors, mas konti pa lang din naman. 2,300, but yung size is 10 micrometers. So we also have here the addressable memory wherein meron siyang 640 bytes. Okay? So that's the processor on 1970, the 4004. The next year, 1972, meron tayong processor 8008. Meron siyang 108 kilohertz, but the bus width is 8 bits. Meron siyang mas maraming transistors and mas maliit yung size niya. 8, I don't know, this nano ba to o micrometers. So yeah, mas maliit and 16 bytes, 16 kilobytes of memory. So mas marami siyang na-store instruction at time. Mas marami na rin siyang transistors, mas malaki na rin bus width niya. But again, the clock speed still remains, no? 108 kilohertz per, 108 kilohertz, or 100,000 instructions per second. Meron din naman lumabas, no? 1974, the same processor, the same name, but different year. Medyo mas mataas na siya. Meron na siyang 2 megahertz, no? 2 megahertz na clock speed or 2 million instructions per second. And number of transistors, dumoble, naging 6,000 na. And yung addressable memory niya mas tumaas. So as you can imagine, as you can see sa ating table, every year na nadadagdag, tumataas din yung speed niya, yung memory niya, yung number of transistors niya. So meron tayong mga formula dyan na ginagamit para ma-estimate nila or ma-calculate nila kung ilan bang possible transistors ang pwede may dagdag sa isang single chip. Okay, so in 1978, meron ng 5, 8, 10 megahertz na CPU. Meron na rin, with a smaller size. No? In 1980s and hanggang 1990s, meron na tayong iba't ibang names and how do you call this? Elements in my CPU. In 1980 pala, no? 1989, umabot na ng 1.2 million transistors ang meron sa isang CPU. So para siyang in a power of 2, no? Raised to 2 lahat ng numbers niya. So sa clock speed, umabot na siya ng 50 megahertz, no? 50 million instructions per second. So gaano kabilis yun sa isang second lang, no? 1990s, umabot na ng 300 megahertz or 300 million instructions per second. Number of transistors, 7.5 million. Meron na rin siyang virtual memory na 64 terabytes and cache of 512 kilobytes in its two caches. Transistors, 7.5 million transistors. Lumabas na rin pala dito 1990 yung Pentium processors, Pentium 1, Pentium 2. So kung 1990, nasa 300 MHz lang. Ano? Ngayong 2024, alam ko meron na tayong 3.5 eh. 3.5 GHz. So 3.5, nasa 3 billion. 3 billion instructions per second. Yan. So that's the how processors are being developed through the years. No? From 1970 na 100 kilohertz lang until 1990 na 300 megahertz. So ngayon 2020s nasa gigahertz na tayo. So let us now watch a simple presentation about the history of computers. It's a 7 minute long And I think this would be the last slide on our uh, subject, our day ngayon. Ano? So after nito, let us stop our class na. Play ko lang to, video number 5.
The history of the computer dates back to the 1800s, when many scientists began to develop various computing machines. However, the modern computer was developed in 1930s, when Konrad Zuse created the first programmable computer, the Z1, which could do additions and subtractions very quickly. In 1941, he created the Z3, known as the world's oldest digital computer. Unfortunately, the computer was destroyed during World War II, but later in 1950, Konrad Zuse used the Z4, the world's first commercial digital computer. Another important moment in history and evolution of the computer was also in 1941, when J.V. Atanasov, a physics and math teacher, and his student Clifford Berry designed a computer that could solve 29 equations simultaneously. However, Atanasov-Berry computer was the first computer capable of storing data in its memory. In 1944, the Harvard Mark I Colossus was inaugurated, a huge computer that occupies an entire room. It was used during World War II to break the complex Lorenz ciphers used by the Nazis. Colossus offered immediate solutions, and it's believed that it significantly shortened the duration of the war. Another computer that stood out at the time was ENIAC, created by John Mauchly and Presper Eckert. The computer was created for ballistic analysis used by the military during World War II. ENIAC occupied a room of 1,500 square meters, weighing 30 tons, and had 6,000 switches and 18,000 vacuum tubes. A few years later, the two built UNIVAC, the first commercial computer for business and government applications. Another important step in the evolution of computers was the time when transistors replaced vacuum tubes. Thus, in 1953, the first prototype computer with transistors was created, Manchester TC. In 1953, Grace Hopper developed the first computer language called COBOL. At the same time, IBM created its first computer called IBM 701. In the early 1960s, IBM launched the 7000 series of mainframe computers that use transistors. The 7030 model, also called Stretch, was part of this series, with 9 such computers being sold to scientific laboratories. The technologies used for this computer led to the development of the IBM 360, IBM's most successful series of computers. Slowly, the evolution of the computer was approaching what we know today to be. In 1965, Program 101 was the first desktop computer sold to general public. It cost $3,200, was the size of a typewriter, had 37 keys, and a built-in printer. At the same time, the world's first 16-bit commercial microcomputer, the DDP-116, was developed and sold for $28,500. The year 1970 is marked by Intel, which launches Intel 1103, the first dynamic access memory chip, DRAM. A year later, IBM invented the floppy disk, which allows data to be shared between computers. Now, who hasn't heard of Altair 8800? It was launched in 1975 and used the basic programming language developed by Bill Gates and Paul Allen. Altair 8800 was a very popular computer, being the model that invented the term personal computer. In 1976, Apple appeared on the computer market with the Apple I, the first computer with a single circuit board and ROM, to which you had to add a keyboard, a power supply, and a case. A year later, they launched Apple II, which was a great success. It was an 8-bit computer and came with a switching power supply, keyboard case, manual, game paddles, and a box containing the Breakout game. In 1981, IBM launched the first IBM PC, officially known as the IBM Model 5150. It was based on a 4.77 MHz Intel 8088 microprocessor and used a Microsoft MS-DOS operating system. This was the computer that revolutionized the development of computers, being cloned on a large scale and thus generating the creation of so many softwares and peripherals. Apple launched Apple Lisa in 1983, the first personal computer to have a graphical user interface. It had a drop-down menu and icons, a Motorola 68000 microprocessor, 1 MB of RAM, a 12-inch black and white monitor, dual floppy disk drives, and a 5 MB hard drive. A year later, Apple introduced the Macintosh, the first successful computer mouse with a graphical user interface and based on the Motorola 68000 microprocessor. In 1984, Michael Dell created PCs Limited, where he created the first self-designed computer called Turbo PC. In the early 1990s, Dell was one of the leading computer developers. In 1987, IBM released Personal System 2, the first IBM system with the Intel 80386 chip. The computer also came with the new operating system, OS/2, which for the first time allowed users of a mouse for IBM computers. The 1990s were marked by an innovation introduced by Apple. Their new iMacs, the 1998 G3, came with clear, customizable case. It was sold for $1,300 and included a 4 GB hard drive, 32 MB RAM, a CD-ROM, and a 15-inch monitor. Apple also marks the 2000s. In 2003, it launched the Apple G5, the most powerful Macintosh to date. The computer had anodized aluminum case and was named the first true 64-bit personal computer. So, in the 1990s, with the advent of the internet, personal computers began to be widely used in all fields. Gradually, computers evolved drastically, both in terms of design and performance. Thus, the market for computer components began to grow more and more, with users being able to create their own PC system according to their own needs. Moreover, it is incredible how from computers that occupied an entire room and performed very simple actions, technology has come to offer us today very small PCs such as the Apple Mac Mini desktop PC system, which offers very high performance when working or doing a gaming session. So we have all the evidence that technology is not standing still, but constantly evolving from day to day. What do you think computers will look like in the coming years?
And so you were able to watch some of our references no, sa ating subject, na history of computer. So, looking forward sa next Monday again. We shall start our class at exactly 6 again. And yeah, I think that ends our presentation today. See you again. Do you have any questions? If you have any questions, please message na lang sa messenger or kay Cha, ano? Kung meron kayong questions. Again, thank you very much for your time and attention. See you again next week.